Okay. So we have Giulio Salvatori now from Perimeter Institute, who will tell us about positive geometries beyond the planar limit. Giulio, please.
Okay, thank you very much. So I would like to begin by thanking the organizers for giving me the opportunity to speak at this incredibly interesting conference. The topic of my talk are going to be positive geometries beyond the planar limit. And as this picture suggests, we're going to see some connection with gravity. It is work based on collaboration with this wonderful group of people. Let me begin by giving a quick overview of the ideas involved. The main actors of our story are so-called positive geometries, which are, roughly speaking, regions defined in the kinematic space of some theory on which the amplitudes depend, and defined by certain positivity conditions. The key feature of a positive geometry is that of having boundaries which satisfy a certain recursive structure, which mimics the type of patterns we see in singularities of amplitudes. For example, a tree-level an amplitude as a pole whenever we put on shell a propagator, and it factorizes there into lower point amplitudes. Similarly, a geometry which is described in an amplitude will have to have a factorizing boundary in correspondence of that singularity. Because of the importance of singularities for the connection of amplitudes with positive geometries, at loop level, we actually make a tactical retreat and consider integrands rather than amplitudes because they have a much simpler singular structure. The precise and quantitative connection between amplitudes and geometry is encoded by the so-called canonical form. It is a differential form which is uniquely associated to the geometry and from which it is possible to extract the amplitude. Furthermore, the canonical form allows to make manifest certain symmetries of the amplitude as well as providing powerful computational tools. The first instance of a positive geometry was discovered in the context of unequal force Young Mills and is the famous amplituhedron. Later, it was understood how a simpler object, a polytope known as a sociohedron, plays exactly the same role in biojoint theory at tree level. It was then generalized at one loop level, and since then we have put a lot of effort in understanding how to go at higher loops. One of the novelties of the story for biojoint theory is that it is actually impossible to go at higher loops without going beyond the planar limit as well. And this is essentially due to the fact that when we cut a higher loop or diagram, we really tend to land in a lower loop non-planar one. So here is a very short outline of my talk. I'm going to start by explaining how we define integrands beyond the planar limit by addressing the famous issue of labeling loop momenta across non-planar diagrams. Once we define our integrands, we are going to see how they are connected with positive geometries, and remarkably, how the extension of these ideas beyond the planar limit is really forcing on us to consider something which looks like gravity. And then I will draw my conclusions. Let's get started. Recently, we understood that it's actually more natural for us to consider what we could call the trace phi cube theory, a theory where we have a single scalar field with two fundamental indices and with a cubic interaction. Amplitudes are then a function of the external momenta, and external particles carries two fundamental indices. We're interested in a 1/n expansion, which is diagrammatically tantamount to replace every cubic vertex with a fattened version of it, thus obtaining instead of graphs, so-called fat graphs. The purpose in life of this operation is to encode an extra combinatorial data, which is an orientation of the vertices incident at the, of the edges incident at the given vertex, and which is inherited by the interaction. There is a famous and classical connection between fat graphs and Riemann surfaces, which goes as follows. We associate a dual triangle to each cubic vertex, and we glue all this triangle according to the connectivity of the graph. We obtain a surface which is orientable, the orientation being induced by the local orientation of each triangle. Because of this connection, we can really speak of genus and other topological properties directly for the graph itself. Here I show two examples where by gluing two triangles in two different ways, we either get a sphere with 3 punctures or a torus with a single puncture. The dictionary between graphs and surfaces allows us to organize the perturbative series for the amplitude in a more elegant way. It becomes essentially a sum over topologies. The first topological feature that we highlight is the boundary type of the surface, that is the number of boundaries and how the external particles are distributed among them. To each boundary type corresponds a unique color factor, which in this case is essentially a product of Dirac chains associated to the external particles. For a given boundary type, we are still left with the degrees of freedom of the number of punctures and the genus, each of which contributes to a different 1/n order of the expansion. Once we strip out all of this information, we are left with a purely kinematical term, a color ordered amplitude, which is given as a sum over all the graphs with that given topology. As I said, we're really interested in an integrand, so we should exchange the summation over graphs with the integration over loop momenta. But to do that, we have to define how to label momenta across different non-planar diagrams. Once again, the dual surface picture allows us to give an elegant formulation of the problem. By routing the momenta in a graph, we're also associating momenta variables to the arcs of a triangulation dual to the graph. These variables are not independent. By momentum conservation, they have to satisfy an equality for each triangle. Now, the space of labeled arcs modulo triangular equalities is really nothing but the homology group of the first homology group of the surface relative to the vertices. Now, you can see that a global routing of the momenta is really essentially equivalent to choosing a basis for this group. Let me illustrate this point by a few examples. We begin with a three-level surface, where a choice of a basis for the homology group is simply given by the collection of the external boundary segments. This is actually another complete basis because they sum up to a circle which is homologous to zero, which is just reflecting the total momentum conservation. Any other arc we can draw on the surface is homologous to a sum of boundary segments, and that same expansion tells us what is the momentum labeling of that arc. When we go at loop level, the boundary segments are not enough anymore. We have to add something else. For instance, in this case, we can add one of the arcs joining the boundary to the internal puncture and associated to that arc the loop variable. Any other arc is expandable in terms of boundary segments and this new arc, and therefore is associated momenta. Similar phenomena happens for every surface. Let me quickly comment on the case of planar surfaces, where a famous solution exists to the problem of loop labeling exists, and consists in associating dual variables to each vertex of the surface and differences to arcs joining them. The reason why this strategy works in the planar case is because there the homology class of every arc is completely fixed by its endpoints. This is no longer true when we go beyond the planar case. Here I show an example where on an annulus I have drawn two different arcs with the same endpoints, but with different homology classes. Correspondingly, they correspond to two different propagators with two different momenta. Now, for any surface, we can find a basis by choosing a triangulation. It's going to be in general an over-complete basis, but we just choose a triangulation. And then every other arc on the surface is expandable in terms of the arcs that form that triangulation. The same expansion again gives us an expansion for the momentum flowing in that arc. By doing so, every Feynman diagram dual to any triangulation on the surface is now canonically assigned loop momenta. The problem, however, is that many triangulations correspond to the same diagram. Here is an example where we see two triangulations of an annulus, which are related by a so-called Dehn twist. If you carefully draw the dual diagram, you will find it in both cases the same. Now, the topological abstraction to finding this perfect one-to-one correspondence between triangulations and graphs is the so-called mapping class group of the surface, which is the group generated by all these twists. So this is the picture that we should have in mind. There is a space of all triangulations on which the mapping class group acts. And it is really an orbit of the action which uniquely corresponds to a Feynman diagram. Then there is an obvious solution, which is just to consider a fundamental domain for the action. That is to say, a set of triangulations which dually contain every Feynman diagram precisely once. Now, imagine assigning some auxiliary variables xc to every arc on the surface and building the rational function obtained by summing over all the triangulation of the fundamental domain and assigning to each of the triangulation the inverse product of its auxiliary variables. From this rational function, we obtain the physical integrand simply by substituting these auxiliary variables with the actual propagator, using the momentum labeling that we introduced earlier. Now, what I've done so far was to define an integrand, but I've not given any compelling argument yet on why this integrand should be any better than any integrand you can define by randomly choosing a momentum labeling. For us, the measure of goodness of our integrand is that it satisfies recursive properties, which, modulo some details that depend on the particular choice of a fundamental domain, follows from a more universal object, which is this master integrand that we obtain summing over all triangulation. It is really a formal object because well, because there are infinitely many terms in the sum. So this is really an integrand which would give infinitely many times the amplitude. But as I said, it has very simple recursive properties. Obviously, we have a pole in this function whenever one of the variable x is set to 0. And the residue of that pole is the integrand that we associate to a surface, to a new surface, obtained by cutting the original one across the arc, which is a quote-unquote Newton shell. So here is an example with an annulus where we see that cutting along this pink x variable, we obtain a disk. All the variables in the original surface which do not cross that arc are meaningful variables on the new surface, while we simply forget about those that cross it. It's essentially saying that we forget about incompatible channels. So from this picture, we see that a double trace integrand has a pole, and the residue is a 3-level amplitude with a particular color ordering, which is dictated by the cutting picture. There is an even more striking recursive effect, and is that any amplitude, in fact, arises as the multiple cut of a vacuum integrand. This is so because we can consider surfaces with no boundaries, which dually gives diagrams, well, vacuum diagrams, and we can cut them into bordered surfaces by choosing a set of arcs. Okay, so now we have defined our integrands, and it is time to see how they are connected with positive geometries. I will begin by quickly reviewing the 3-level story. The first and most fundamental fact is the existence of a polytope whose faces are in one-to-one correspondence with the singularities of amplitudes. Attached to this polytope is its canonical form, which is defined by requiring it to have singularities only at the border of the polytope. From the canonical form, it is possible to extract the amplitude, and indeed one way to compute it matches term by term the Feynman diagrammatic expansion. Now, the canonical form has an interesting symmetry. It is projectively invariant, which means that it is invariant under local rescaling of the propagator variables. This is equivalent to say that it doesn't have a pole at infinity, and so is made manifest by the existence of the polytope that manifestly doesn't have a border at infinity. However, this fact is obscured by the Feynman diagrammatic expansion because each term individually is not invariant under this transformation, which means that it has a pole at infinity. And it's really thanks to a conspiracy, a non-trivial conspiracy among the relative signs of the contributions that this pole cancel. If we want to make manifest this fact at the level of the form, we are naturally led to new representation of the form and therefore of the amplitude, which are more similar in spirit to BCFW recursive formula because, well, because they are recursive and because they introduce spurious non-local poles. Okay, finally, from the existence of the polytope, it also follows the existence of a complete fan. A fan is a collection of cones, and to say that it's complete means that the collection of cones tile completely the space. No direction is left out. Everything is inside of a cone. This particular fan is labeled by Feynman diagram. Its cones are labeled by Feynman diagram because it is the dual fan of the polytope. While it is always true that from a polytope we can obtain dually a complete fan, it is not guaranteed that a complete fan arises as the normal fan of a polytope. In fact, for this particular story, the two facts are completely equivalent. This is due to a certain two-dimensional space-time picture, which, starting from the fan, allows us to build back the polytope. I do not have the time to review it, but it has been explained by Nima in previous talks. Now, in a sense, these 3 points of view are completely equivalent, but the one which is more convenient to start from to generalize the story at higher loops is the one coming from the fan. And the reason is that the fan has a natural generalization for every surface. It is the so-called tropical Teichmüller space. I do not have the time to explain the deep mathematical origin of this space, so I will content myself by giving you an operative definition to construct it. We begin by choosing any triangulation of choice on the surface of interest. Then we associate to every arc of the surface a vector which records the intersections of the vector with the underlying reference triangulation. In order to make sense of the intersection at the vertices, we slightly push the endpoints of the arc, obtaining what is technically known as a lamination. Now, this procedure assigns a non-trivial vector also to the boundary segments, which are deformed in this way. Recall that dually, boundary segments correspond to external x, so we would really like them to be 0, to be on shell. The theoretical way to do that is to define a projection, which is a projection through the boundary segments, that is, it kills the boundary segments. We define this projection and we apply it to all the other rays. By doing so, we get a new collection of rays which for the people familiar with the topic are the G-vector of the cluster algebra associated to the surface. Finally, we build cones by taking convex hulls of those rays which correspond to a full triangulation. The collection of these cones is the tropical Teichmüller space. Now, in the case of a surface with a trivial mapping class group, the fun is complete. Once again, this is really a consequence of the existence of the polytope, but it is also something that we could discover independently. In fact, one way a physicist would discover this would be summing over Feynman diagrams, which I recall you, they are dual to triangulations and so are associated to cones. We start from a Feynman diagram and we add all the cones summing over all Feynman diagrams. When we're done, we find that there is no hole in the space, everything inside the sum of the cones. When the surface has a non-trivial mapping class group, however, the same procedure doesn't work. It would produce a never-ending collection of cones which asymptotes towards certain directions which are missed. This ray is outside all of the cones. Note that, in fact, that ray corresponds to a closed loop on the surface, which is not dual to a propagator of any Feynman diagram. Now, because the fun is not complete, it's not possible to find a polytope associated to it. It's not possible to find a meaningful projective form, or for what it matters, not even a meaningful integrand. However, our physics perspective tells us the natural thing to do. We simply stop after a while. When we see every diagram, or more precisely, when we see the integrand a number of times, let's say m, we simply stop adding cones. We are left with some hole that we fill by adding cones built out of this missing direction, which we call delta cones. So like this one and that one. We get a new complete fun. It's not the tropical Teichmüller space anymore. It is associated to a polytope and to a canonical projective form. The form will contain multiple times the integrand plus an extra funny term which is proportional to 1 over delta. Now, our original purpose was just to obtain the integrands, and for that purpose we're done because we can simply send to infinity delta, which kills this extra term. However, this destroys this projective symmetry, and at this point it is only natural to ask ourselves what is the meaning of this full object which carries this hidden symmetry we discovered at tree level. In order to gain some insight into that, it is convenient to study the geometry of the delta cones, or equivalently, dually, the geometry of the delta facet to which they correspond. What we have found is that this thank you very much. What we have found is that this facet once again follows a certain recursive structure, which is once again dictated by the surface. This time, instead of cutting along an arc, we are really pinching it. The crucial difference is that by pinching, we do not produce any extra boundary, but rather we produce a new puncture. To be more explicit, what we have found is that to every surface corresponds a polytope, and that polytope has a facet corresponding to delta, which is obtained by taking the product of the polytopes associated to the pinched surface and projecting them on a subspace which corresponds to glue them together by the puncture. Finally, in this particular case of the annulus, note that the loop is homologous to one of the boundary components, so it is naturally associated with the momenta, which is the total momenta flowing through one of the boundaries. Putting all of the things together, we understand what is the meaning of this extra term in the form. It's putting a pole, which corresponds to putting on shell a particle which doesn't carry a color, because putting on shell that, we do not get a new boundary segment. Boundary segments correspond to colored particles. So it really looks like in order to complete the fun, we're really forced to complete the theory by adding something which looks like a graviton, more precisely a dilaton, since we do not have spin. Okay, now I've shown this example in the case of the annulus, but it's really a part of a larger conjecture, which we have checked in many non-trivial examples. The parameter that controls the difficulty of the problem and the richness of the geometry is how many deltas we have. So there is a set of surfaces which have finitely many deltas and that we have completely under control. And then there are all the surfaces which have infinitely many deltas. And for those, we already have some preliminary results, so we're confident that we're getting there. Okay, finally, let me quickly mention some implications of the projectivity for the actual computation of the amplitude. As I said, projectivity is obscured by Feynman diagrams, but we can simultaneously make it manifest and obtain a recursive formula by triangulating our polytopes in intelligent ways. Just to show you an example, in the case of a double trace integrand, we found a triangulation of the corresponding polytope by projecting on this extra new delta facet. It gives a recursive formula in terms of three-level colored amplitude, whose color ordering is once again dictated by the cutting picture. Okay, let me draw my conclusions. The first and foremost message I wanted to pass is that we're getting closer to having a full amplitude-hadronic picture for phi to the cube theory. Along the way, we found a meaningful definition of non-planar integrands, which in fact we expect will carry over to every kind of field theory, was Feynman rule gives some notion of a cyclic ordering of the edges at the vertex of interaction. So for example, pure Yang-Mills. We get new recursive formula, and perhaps most intriguingly, we have this surprise that we find a positive geometry embodiment of what has been the current, well, the leitmotif of this conference, that is QCD meets gravity, and in fact, in our case, it really needs gravity. And then maybe I will just stop here and ask for questions.
Thank you, Giulio, for a nice talk. So I guess we have a couple of minutes before the closing. So anyone has some questions? Yeah.
Yeah, so did you try, so your new definition of integrand, did you try to apply it to some simple example we have been struggling with like for many years, like the 4.1 loop? What exactly does it give you, like in the context of Yang-Mills theory or gravity?
Okay, I have to say, I have to shamelessly admit that we have not tried anything other than this biojoint, quote unquote, biojoint theory yet. And so, yeah, I don't know. But once again, if you take Yang-Mills, you know, this ribbon, this fat graph story is simply the third double line notation, so it should really carry over in the same way. But yeah, we have not tried yet. So.
Yeah, I just wonder, does it correspond to, because there is one definition of the integrand, which is just sum over all labelings of internal edges. This is one definition. It has some good properties, it has some bad properties. Is it that in that particular case or not?
No, I don't think so, because, well, in fact, our integrand depend on a choice, which is the choice of fundamental domain. So for a surface, okay, we can in principle associate many. Okay,
maybe because you haven't done it, but yeah. So does it mean like choosing an origin? So you are actually, okay, maybe I can talk later. Yeah, I would just like to know what exactly, how do you make a choice of the loop momentum in this just simple example when you obviously totally have to make some choice, yeah.
Yeah, it totally does involve a choice of the origin, but
okay, I see.
Which is what Giulio described as choosing a basis for that H1.
But there really is an invariant object. I mean, the actual homology is totally invariant. Yeah, choosing a loop momentum is just choosing a basis. That's all. I think it's not what you're interested in, Yara, for gravity or even for Yang-Mills, where you keep the FABCs in. It's really tailored to the genus expansion. It's really tailored to the fat graph expansion. But
yeah, so it doesn't kind of answer the question if I want to sum the diagrams together.
Yes, it's completely meaningful to sum the diagrams together. That is the point. But it's meaningful in this 1/n expansion. So order at any order in 1/n, there's a perfectly well-defined integrand. In fact, there's a number of well-defined integrands. That's sort of part of the point, because exactly the same variable, exactly the same propagator can be represented in different ways that differ by shifts of loop momentum. That's what Giulio was saying, that you have to make a choice about how to keep one copy of all the diagrams. But having done that, the choice of loop momenta is totally fixed. Yeah, there's a slightly more natural object, which is what he mentioned, to sum over everything. Then you get, it's a kind of a formal object because it's infinity times the amplitude. But that's the thing that you can do, which doesn't involve making any choices. But once you do make a choice about which diagrams you want to keep, the loop labeling problem is solved. That is solved by this picture of the homology of the surface.
Yeah, in this summing over everything, the problem is that like different cuts or the same cut is represented in many different ways.
That does not happen here. That's really the point. That is really the point.
Yeah, okay. I would love to see some details about how to do it.
It's just it's not what if you're interested in gravity, we don't have the analog of this genus expansion. But for Yang-Mills, we do, and then it's completely well defined.
Okay.